Okay, so let us start with today's lecture, which is on contents of your week 2 for the course ME75, that is Foundations of CFD. So, this week mainly how to select the computational domain for the CFD analysis, and then how to perform the discretization, and what type of mesh you should select for the given problem, and what are the different possible finite difference formulations on that particular grid was discussed in the contents. So what I will do is I will briefly I'll briefly recap the contents of your week 2, and then probably start with the questions. Okay. So these questions will be similar to your questions in the assignment, but they will not be exactly the same. They will be similar. Okay. So you can ask any queries regarding these questions if you have uh, in the chat box. Later on, I'll allow you to speak also. That time you can directly speak and ask to me. So that is also possible. Okay. So let me just share my screen now. So is my screen visible? Can you people just reply on the chat box whether my screen is visible or not? Okay, okay, thank you. Okay, so let us get started with this week's content. So, as I said earlier, so the contents are mainly based on computational domain, creation of computational domain, and selection of the grid for this computational domain, and how we perform the discretization. That is how we try to convert the governing equations into a set of solvable linear algebraic equations. That is done using the Taylor series. Okay, it is just a tool uh, to perform that operation. Okay, so just let me introduce myself again for those who have joined for the first time. Okay, so my name is Sumant Murab. I am a PhD research scholar in Department of Mechanical Engineering at Indian Institute of Technology, Bombay. So mainly I work in development of CFD codes to solve biomedical problems, mainly the problems which involve sound generation due to irregular blood flow in arteries. Okay, so that is my main PhD topic. And my PhD supervisor is Professor Atul Sharma, and co-supervisor is Professor Janani S. Muralidharan. So I hope that my voice is clear. So please let me know if there is any issue with my voice. I mean, I hope that it is clear and clearly audible. Okay. So please let me know on the chat box whether it is clearly audible or not. Okay. So if there is anything, we can adjust. Okay. So okay. So I don't see any messages on the chat box. Okay. So last week we had just got an introduction of CFD, and then mainly we had seen briefly what are the steps which are there in CFD. So what are the steps which you have to be following, and then mainly we looked at applications of CFD, because before getting into a subject we have to first understand what is the subject about and why we have to study a subject. So you need to understand the applications for that. So we just went on to see what are the practical applications of CFD, and specifically I had taken example of biomedical problem, wherein we saw that using computational fluid dynamics we were able to come up with a better design of a stent which will help to unblock a blocked artery. Okay, so how we can improve the design of that particular stent. So that is what we had looked at. the as an application of CFD. Um, and then we had also looked at the governing equations. Okay, so what are the different governing equations which you will be solving to obtain the fluid flow solutions. Okay, and then we also saw some flow tracing uh, tools, that are the streamlines, streak lines, and path lines. And then what is the advantage of performing non-dimensionalization. So that also we had seen in the last week. And finally, I think in week one, you were also exposed to some of the benchmark problems which are there in CFD. I mean, once you develop any code, once you come up with a numerical methodology and write the code, you have to test whether your codes are really giving correct answers or not. So for that, we do the benchmarking of our codes. So for that, what are the different problems? For example, the lid driven cavity problem, wherein there is a cavity which is like a box, and then there is some fluid which is filled inside the box, and the top part of that box you are moving with a constant velocity. Okay, so then what will be the flow patterns which will come inside that box? So that is one of the major benchmark problem, I would say, in CFD. So apart from that, you had also studied some 2 3 examples. So overall, you had got a brief introduction to CFD and its application areas. Okay, so from week 2, the actual contents will start. Okay, so as I said in the last week, okay, so mainly you have three procedures, three steps in CFD. Okay, the first one is pre-processing. Okay, what do you do in this pre-processing? First, you see the problem, okay, which is there in your industry or in your study area, whatever. Okay, so you see the problem and you see what physics you have to apply. Okay, you see what physics you have to apply. By what physics I mean what governing equations you have to apply. Okay, that is the mathematical model. What governing equations? So usually it is a Navier-Stokes, but you can again approximate Navier-Stokes. So for example, if the flow has very less viscosity, then you can ignore the viscous terms and then come up with Euler equations. Okay, so that is the physics. Then in pre-processing, you also have the part of selecting computational domain, which we will discuss in this week's content, the week 2. Okay, so you have to uh, finalize, you have to select what domain I have to study. Okay, this is very important, we'll go in deep, okay, in this week's content. Okay, so that is the pre-processing. Okay, and also the grid generation, which will again look in today's lecture. Okay, now apart from this pre-processing, okay, you have mainly the solution. So solution methodology, so the way in which you will solve these physics in this computational domain with this particular type of grid. Okay, so that will come mainly in solution. So at the end of today's lecture, we will see all these processes. Okay, the pre-processing and then the solution on a 1D heat conduction problem. Okay, we will see just a 1D heat conduction problem and how we will apply these techniques for that particular problem. Okay, and then finally you have post processing also, which we might not deal much today. Okay, post processing, so once you get the solution, say for example temperature. Okay, so now you have to analyze what is the heat transfer. So in industries you will all mostly need the value of heat transfer. So using a particular type of fin, I want to enhance the heat transfer. So temperature is not required there. You want to calculate what is the amount of heat transfer happening through that by applying that design of a fin. Okay, so there you need to again calculate heat transfer rate from the temperature which you get as a CFD solution. In CFD, you will always, as a CFD solution, here you will always get the flow variables and the temperature. Okay, U, V, W, it is the velocities and the pressure. okay, and you will get temperature. So these quantities you will get, but from these quantities you have to calculate what is say heat flux, okay, then you can calculate Nusselt number. These are some basic things in our fluid mechanics and heat transfer, okay. So you might be interested, for example, if you are trying to do a flow over an airfoil, okay, now we want to optimize the lift over this airfoil structure, okay. So for this, if you just see the velocity, it might not be useful. Can you people guess what might be important here for this particular kind of problem? We will get velocity from the CFD, okay. Now from velocity, what should we calculate to see whether the we are getting a improved lift or not? Which parameter we have to calculate? Can you write on the chat box? Can you just guess? This we see pretty commonly in our fluid mechanics also, okay. Yeah, it's the pressure distribution. From pressure distribution, which parameter do we calculate? Can you write down that? Like for example, we are calculating the heat flux, right, from the temperature gradient. Okay. So similarly, what parameter do we calculate in order to compare between, say, I have two configuration. I have one symmetric airfoil here, or just a flat plate, say. Okay. Yeah, surface forces. Uh, so surface lift force you are trying to calculate, and then when you non-dimensionalize that surface lift force, you kind of get lift coefficient. Okay. Now this lift coefficient value, you kind of compare it with different configurations. Okay. So you need to calculate this using the surface forces, rightly as you have rightly mentioned. Okay, surface forces are again calculated using the pressure and the velocity gradient. Okay, the sigma xx, for example, minus p plus mu into du by dx. So in that way you are calculating this surface forces from which you are getting this lift coefficient. Okay, so those things come in post processing. This we will not see much today, okay. uh, but we will mainly take an example and see how to do pre-processing and solution today. Just it's a we will do just a, pen and paper based calculations, okay. So from next week, once we are quite confident with the pen and paper calculations for small problem, then we can really go into coding and see how to apply them for large problems, okay. So then only we can understand the coding aspects very clearly if we are confident with solving small problems on pen and paper, okay. So that is the first step. I think that is the first step in whatever subject you are learning, okay. So I hope that that point is clear, okay. So yeah, so just I'll just recap the week 2 contents. So mainly the computational domain. How do you choose a computational domain? So this is the first point, okay. So for example, assume that you are just performing a flow in a channel, okay. This is just a 2D channel. These are parallel plates, okay. Here it might not be exactly parallel. Okay, these are two parallel plates, okay, and this makes a channel. This makes up a channel, and from the left you have a flow which is coming in, and from right it is going out. So mainly it is quite simple here that you kind of choose this rectangular box, okay, as a domain. There is not much to think about in this case, okay. uh, but a major thing which you have to think is you know the diameter, sorry, the height of the channel, okay. You know the height of the channel, but when you are selecting a computational domain, okay, so computational domain means it is the area in which you want to finally get the flow variables or and the temperature, okay. Say velocities and pressures you want to get, in which region you have to get, okay. So say I select some rectangular region like this. I already know the height of this, but how do you calculate, how do you know which length I have to, what length I have to take, okay. in an industry problem, it might be already given, okay, so that I have a pipe or a channel which has this much length, okay. But if you are trying to study the physics of flow in a channel, you want to say uh, where the the parabolic profile is reached in a channel, okay, those things if you want to see, then what length will you select? Can you write on the chat box how do you select the length of this domain, so that you kind of understand all the physics which is happening in the particular case study. So you are just simulating a flow in a channel, okay, and you have to select a length. You cannot select randomly very big length also, that will increase my computational time, because more number of grid points will be required. So you have to select an optimal length. So how do you select that optimal length? That is the fundamental question here, okay. Oh, grid independent study. See, grid independent study, I will just discuss it next. Okay, it is not relevant to selection of domain length. It is relevant what you are telling to select the grid size. Okay, grid independent study we do it to select the grid size. That I will discuss next. But before that, I have to select the domain, right? I have to just select what is the this height anyway. I know. I have to select the length for performing simulation. After that, I will do the divisions and generate the grid. That is a secondary thing. But first, I want to kind of see what length I have to take. Yeah, it should not affect the your flow variables. Okay, because we are selecting an outlet model here. So how do you know that the flow has kind of stabilized? Okay, let me ask it in that way. Maybe so basically you have a very flat velocity profile in this channel at the inlet, okay. After that, uh, there is some boundary layer which comes in, you get some profile, and after that you get a parabolic profile. So at what length should you stop? Okay, let me ask like that. Okay, so that the wake field is uniform. In this, I don't think you'll be getting a wake. It is just a straight channel. Okay, so if you have some different channel configurations, which I'll discuss in the next section, there you will get a wake. Okay, so yeah, but what you are trying to say, that is that I can understand, it is correct. The thing is the so Ayaz Khan, he has said fully developed flow is reached. Yes, that is the correct answer. Okay. So what you people were telling, that was also correct. I mean, but for this particular case, for this channel flow case, the answer is that the flow should reach a fully developed state. Okay, so what will happen after reaching a fully developed state here is that the velocity profile will reach a parabolic profile. Okay, this is a channel, simple channel problem. After this length, the flow field will remain constant only. Okay, it's just that the pressure will just drop linearly, that is not required. Okay, the flow, it will remain same, there will be no change in velocity, but here there will be a changing profile. Okay, there will be more flat. Okay, here it will be completely flat. Okay, but after this the flow will kind of remain same. So we are not interested to see this picture at all. Okay, why do you want to see this picture? It's not changing. Okay, so only things change in this particular domain, so it is better to only select only this particular domain length. So that is the optimum length. You can select more also. Ideally we select to some extent higher length, but you cannot go to a very large extent also, because what will happen is that you need to discretize this. That is the second step. So you need to divide this whole domain into small number of elements. Okay, which is called as grid, which you have already learnt in the week 2 contents. Okay, now if I take a very long length, I will get more number of elements, which will increase my computational cost also, the time required to solve the problem. So I have to take an optimal length. So I take that fully developed length. Okay, so yeah, so that is the thing. So as I said, the second step will be after taking the uh, domain. Now you have to decide what type of grid I will take and what are the number of grids. So first let me touch upon uh, what type of grid do you take for this particular problem. So this is just a rectangular channel. So it's the domain itself is a rectangle. So here you can have just a very rectangular kind of division of this whole rectangular domain. Okay. Now I just divide this, okay, very uniformly. By uniformly I mean, what I mean is that the distance between these two lines will remain same here, here, okay, that is uniform, and in the y direction also it will remain same, delta y we call it as, okay, okay, here delta x, that will remain same. So I will divide it in this form. So this is a very structured mesh. That is the first type of mesh. Okay, I will later on define what is exactly meant by the structured mesh and unstructured mesh, but you have a very uniform kind of division. Okay, now I'll take another example. Okay, now this is just a blocked channel. Okay, the blockage is at only at the top wall, assuming that. Okay, now in this you cannot have exactly these rectangular kind of cells, okay, wherein we want to solve. So we just make a curve of this particular mesh. Okay, so we can generate, this is one type of method wherein you can generate. Okay, again this is a structured mesh only, this is not an unstructured mesh. Okay, you have to be very clear about what is structured and what is unstructured mesh. This might look like unstructured, but this is a structured mesh only. Okay, so but this is called as a curvilinear mesh because it is curved, the mesh is curved, and it is actually a body fitted curvilinear mesh because the body has a curve here, the channel has a curve. Okay, so this mesh is also adapting to that curve. Okay, so that is why it is called as a body fitted mesh or a curvilinear mesh. Okay, but it is a structured mesh again. Now how do you identify whether it is a structured mesh, whether the mesh is structured or unstructured, and when do you choose unstructured mesh and when do you choose structured mesh? So that is the final discussion before going into the Taylor series. Okay, so there are two aspects. Okay, the first aspect is you draw these lines in the domain. Okay, this mesh lines, whatever you call it as, so they intersect. Usually they are known as grid points or nodes. Okay, whatever it is, based on the type of discretization, you know. So you have to see what are the number of neighboring nodes for this one particular node. Okay, so yeah, this uh, lecture is being recorded and it will be posted on YouTube. Okay, so I'll just give the link of the YouTube also, YouTube link where this will be posted. Okay, you can just go and check it out. Just put, okay, just give me a minute. Okay, so yeah, this will be posted, and the lecture slides also will be posted. Okay, so I'll just give the link to that also. Yeah, the lecture slides and the video, both of these will be posted. Okay, yeah, so where was I? So you have to see what are the number of neighboring nodes for this one particular node which I have marked as cross here. So if they are same, okay, here I have 1 2 3 4. Okay, there are 4 neighboring nodes. Now if I'll take a second other node. Okay, now I will count the neighboring nodes. Again there are 4 neighboring nodes, so it is always 4 4 4. Okay, for all the nodes you have neighboring nodes, the number of neighboring nodes as 4. So this is a structured mesh. Okay, this is a structured mesh. Now for example, if you had a same domain and if you had a, say, a triangular elements which are randomly arranged here and there. Okay, okay, so this is how they are arranged. Now you can see that this particular node where there is an intersection, it has like around 1 2 3 4 5 neighboring nodes. Okay, whereas if you take particular this node and assume that it has like this connections, so something like this. Now this particular node, it will have 6 neighboring nodes. Okay, whereas this had only 5. So you have 5 and 6. So these are different. So this is an unstructured mesh. This is an example for unstructured mesh. So that is how we usually define it. But in the weekly content also there were some other definitions also, which I hope that you have seen. Okay, this is one definition in which through which we kind of define. Okay. So I hope that there are no queries. So till now we have discussed how to select a computational domain depending on the problem, and then once we select a computational domain, optimum computational domain, then how do we mesh it? Okay, uh, there are two types of mesh, structured and unstructured. And one thing which I forgot to say is that, see, for these simple examples you can go with a structured mesh, or even a curvilinear mesh for this blocked channel or something. But if you really have a very complex kind of structure, okay, very random kind of a domain here, okay, inside that again you have some solid particle here. Okay, now this is your flow domain. Here it becomes very difficult to generate these curvilinear meshes also. And what happens is that the elements become very small. If you have a curvilinear mesh, it might lead to some convergence issues. Okay, so usually you go with unstructured mesh here. Okay, so till now we discussed what are the different type of mesh and when do you use certain type of mesh, whether you want to go for structured or whether you want to go for unstructured. So are there any queries regarding this discussion regarding the computational domain selection and regarding the mesh generation? You can post them on the chat box. Okay, if there are any queries. Okay. So I hope that there are no queries. If there are any queries, you can mail me also later on. I'll just share my mail ID also. Okay. So again, like last week, what I had done, I had compared the computational fluid dynamics process with a video capturing process through a video camera. Okay. Last time also we had done this. Okay. So I'll just explain the mesh terminologies with respect to this video camera. Okay. Now you want to kind of capture a particular region. Okay. You can only capture a particular region in a video camera. You cannot completely capture everything. Okay. In one particular frame. Okay, so that is your computational domain. That is the region being captured by a camera. Okay, so that you can see in this figure. So that is how you define the computational domain if you want to relate it with the camera. Now, the grid points, or in finite volume method we call it as control volume. In finite element method we call it as elements. Okay, so these are nothing but the pixels of a camera. Now, camera also has a resolution, right? Like now how many pixels are there, basically how many points the screen is divided into. So how many points the picture can be divided into, that is a pixel. Okay, those are the grid points. And resolution of a camera is nothing but the grid size. Resolution means you say 40 mp, so there are so many pixels. Okay, 40 megapixels are there, so that is the grid size. Okay, so the grid size we usually say 100 cross 100. Okay, you can call it as say 10,000 also. Okay, that is the resolution. Okay, resolution of your computational domain, by how many points you have divided your computational domain. So if you relate it with camera, it is a resolution of a camera. Now when you are especially doing unsteady simulations, okay, you need to select something known as time step size, which is very very important. We will come to this in maybe next week's content or so. So you have to select a time step from which you have to jump. So I can jump from zero point 0.1 second to 0.11 second, then 0.11 to 0.12 second. I cannot directly jump from point 0.1 to point 0.2. I may miss a lot of information. Okay, you have to select a time step size. Now that is equivalent to the fps of your camera, the frame per second. Okay, how many frames it can capture in 1 second. So that is your time step size in the cfd terminology. Okay, so these concepts I have mainly borrowed from my professor's book, textbook. Okay, by Professor Atul Sharma. He had written a book on Introduction to CFD. Okay, so there also these terminologies are given. How we can relate a camera to CFD. Okay, so for just for better understanding. Okay, so that you people can remember it easily. Okay. So that is about the computational domain and the grid generation and grid selection. Okay. Uh, Now the second thing is you have generated the grid. Okay, you have selected the grid. You know how to do the grid generation, everything. Assuming that these things will be dealt in detail. Okay, these are just the like these are just we are just explaining the steps here. In detail how to generate the grid, those things will be dealt in the next classes. Okay, so assuming that you have generated a grid now you have to get a linear algebraic equation of the partial differential equation, because linear algebraic equations you can solve. Okay, I don't know, you might have to search for the PDF of the book. Okay, not really sure, I have a hard copy, but it might be available in your college library also, I don't know. But anyway, I'll give the book details. Okay, you can just go and see. It might be available on Kindle also, I don't know. Okay, yeah. So once you generate the grid and you have the physical model, the mathematical model, you have to come up with a linear algebraic equations. Okay, so how do you do that? How do you convert a partial differential equation into a linear algebraic equation? That is done through an operation called as uh, discretization. Now there are three different types of discretization, which I will just discuss in first question. Okay, which is there in the next slide. Okay, but all of this discretization will ultimately lead up to a gradient of some variable velocity. Okay, du by dx, everything something will come through. Okay, finally you will end up there, du by dx, dt by dx somewhere. Okay, now you have to convert it into a linear term. So that is done using the finite difference, okay, formulation, and that you will get from Taylor series. Now I'll explain how you will get that. Okay, this you might have seen in the weekly video content also. I'm just revising it. Okay, so in the Taylor series, what do we do? We get an expression for a function at x plus h. H is a small increment from x. Okay, so I want to calculate a variable at say 2.1, a function say e raised to x. I want to calculate at x equal to 2.1, but I know the value at 2. Okay, so 2 plus zero point 0.1 I try to do. Okay, a function at x plus a small increment of that. Okay, x plus h. I calculate it using the known function f of 2, that is e raised to 2, which I already know, plus this terms. This is the Taylor series expansion. Now f dash is the first differential, that is dou f by dou x, f double dash dou square f by dou x square. Okay, so that is the basic meaning. Okay, so that is how you will get f of x plus h. So similarly we will get f of x minus h. So now what we want, we actually want f dash of x, f double dash of x. This is what we are interested in. We already know f of x plus h. Okay, so these are the linear terms. Okay, and this is what we want, f dash of x. So for example, in this case we can just do an addition to get f dash of x. Okay, then we can do the subtraction to get f double dash. Sorry, if you subtract you will be getting, I think, f dash of x, and if you add them up you will get f double dash of x. So these are just the simple things, but these are valid only for very small order differential. This is not a general method. This is like just a trial and error kind of method, wherein you will get f dash of x, f double dash of x by doing manipulations, okay, manipulations of this Taylor series expansion. So that is the first method, wherein you will get this f dash of x, f double dash of x. Okay, so this is just one method, but if you want to go for higher order differential, f triple dash of x, and one more thing which is very important to note in this Taylor series is the truncation error. So for example, if you have calculated dou square u by dou x square or something like this, and there are some terms which kind of remain off, okay, in the previous slide also if you see, there are like f triple dash of x, which kind of remain out, okay, f double dash of x, here it remains out, okay. So with respect to that, you will have something like h square, here it is written as delta x square, okay. Accompanying that will be this term, okay. So you have to see what is the order of this. It is the second order, okay, it is delta x square. So here that the minimum truncation error has delta x square, so there will be truncation error which will have delta x raised to 4 also in the front, okay. But the minimum truncation error that has the order of 2, okay. So this becomes a second order scheme, so that is why we call it as second order scheme. So that is one terminology. The second thing is whether it is a forward difference or whether it is a backward difference. Here we have the grid point, so once we generate the mesh, especially the structured mesh, we give some indices 0 1 2 3 4 in the x direction, 0 1 2 3 4 in the y direction. So these are just the indices I and j, okay, in x direction and in y direction, okay. So here I plus 1, I minus 1 both are there, okay, for I comma j. So both left as well as right both are there, okay. So it is a central difference, that is why we call it a central difference. And the minimum truncation error has a order 2, so it is a second order central difference scheme, okay. That is how the difference schemes are defined it as, okay. I hope that this point is clear, okay. That is why we call forward difference first order forward difference, second order forward difference, second order backward difference. So that is how we call it as. Now as I said, this method of doing manipulation to the Taylor series to come up with this equation, this can be easy for these lower order schemes, first order, second order, okay. It is easy for them. If you want to go for higher order and for higher differential, okay, then this manipulation becomes quite difficult. So we have some other approaches, amongst one which you have already learnt in this week 2 content again, that is a polynomial approach. And there is one more approach which I feel is more simple, more easy, that is not there in the week 2 content, okay. This is completely optional and I will just discuss it, okay. That is called as a Taylor table approach, okay. This is not there in your weekly content, but it is very easy, especially I feel it to be very easy to calculate the higher order differential, okay, and higher order schemes, okay. So you just assume that f dash, okay, now I am calculating f dash. Similarly you can do for f double dash also, plus the summation of akf I plus k. Now how do you decide this k, okay, k is equal to 0 to n. How do you decide this n? This is based on the order. So for if you are doing say forward difference, um, okay, just if you are doing forward difference and if you want an order 1 forward difference, so you take only I plus 1, so n will be equal to 1 in that case, okay. So that will be the case, n will be equal to 1. If you want a second order scheme, you need to go till I plus 2, okay. So n will be equal to 2. That is how you decide upon the value of n, okay. 0 to 1 for first order, for second order 0 to 2, something like that, okay. This is how you define this equation. Now you have to find really ak, that is what you have to find out, okay. Now what we do in this procedure is that, say for example I know the number of k's which I need. So for example second order, if I want, I will be needing a1 and a2, those are the things, and fi plus 1 fi plus 2 for second order scheme, right? So I need till I plus 2. So I really define this f dash I, then fi plus 1 fi plus 2. That is how I write in these columns. And then The Taylor series, you expand it in terms of fi dash, fi double dash, and fi triple dash, right? So similarly I write the columns, but you can see that the number of rows should be equal to number of columns. Now I know the number of rows because I know till what point I have to go, because I know the order which I want to get. Okay, so then you can restrict till, say here I have restricted fi triple dash. Okay, so that is the thing. So now you have to just go on writing the Taylor series. Now fi dash will be equal to nothing but fi dash 1. So 0 1 0 0. Now if you go for fi, okay, it will be nothing but again fi. So 1 0 0 0. So something like this, and multiplied by a naught because you have a naught here. Okay, now fi plus 1. How do you write fi plus 1? If you are expanding the Taylor series, you get fi plus h into f dash of I. So here it will be 1, okay, and here it will be h, and then again multiply it by a1. Okay, a1 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 a1. So that is how you write down. I hope this is understood. Okay, so similarly you write the Taylor series expansion for fi plus 2. Okay, once you form this table, then everything is very easy. Now what you have to just do is that you have to add these things, because that is what you ultimately want. F dash of I plus summation of this ak into fi plus k, so is equal to all these terms. Okay, a naught plus a1 plus a2 according to the columns, okay, into f of I, the column head, into f of I. Okay, these sorry, these column elements into this head of the column. That is what I have done here. Okay, and then similarly for the second column, third column, fourth column. Okay, then you will see that these things should go to 0 because I have written here 0. The right hand side is 0. So for that, this all these things should go to 0. A naught plus a1 plus a2 is equal to 0. 1 plus a1h plus 2h a2. So these are all 0. So you solve these equations. Okay, so that's the whole thing. So how many these things you have? You will get so three terms, and with this you will get three equations also, you can get very easily. So just solve these three terms and three equations and three unknowns. You will get a naught, a1, a2. That is the procedure. So once you find a1, a naught, a2, so you have found out the expression for fi dash. Although this might look a bit lengthy, but this is very easy to do. I mean, it is just mathematical thing you have to do, but you need not remember anything. So those expressions for fi double dash, third order accuracy, if somebody asks, so you cannot remember those things, right? So this I found out to be one of the easy approach. Okay, so okay, so we have discussed mainly discretization, how we come up with term fi dash, fi double dash, and what is the second order, what is third order, and what is forward backward. So are there any queries in this particular discussion? You can post on the chat box. Okay, so after this we will get started with the problems. So in between, if my voice also, if it drops off, then please let me know in the chat box. Okay, so sometimes my earphone connection is not very strong, so um my voice might drop off. So if it drops off, then please let me know on the chat box. Okay, I'll be seeing the chat box. How do we get the table values? Okay, so these table values, you mean to say these values, like the elements of this table? Is that what you are asking? Okay, so these values, yeah. So as I said, you these values are got using the Taylor series. Okay, so first let me explain from the first row. Fi dash will be nothing but fi dash. Okay, 0 into fi, 0 into fi double dash, this 0. So it is nothing but fi dash is equal to fi dash. So similarly fi is equal to fi, so these terms will be 0. Okay, these two things are simple. Okay, uh, I hope this is clear. Only thing is you have to see how to write this third row and the fourth row elements. Okay, so this we have written it using the Taylor series. Okay, so now just let me explain for the third row how I have written down. Okay, now fi plus 1, it is right. Fi plus 1 is equal to fi plus h into f dash at I plus h square by 2 factorial into f double dash of I. Okay, this much I know, plus again f triple dash will also come. Okay, let me restrict till here. Okay, now you already know that it is multiplied by a1. Okay, so just multiply LHS and RHS by a1. Okay, so f of I is now multiplied with a1. Okay, so that is what I have written, a1 f, because f of I is there, so it's a1 into f of I, a1 h into f dash of I, a1 into h square by 2 factorial into f double dash of I. So a1 into h square by 2 will be this particular element of this table. So that is how we kind of come up with the elements of this table. Is that understood, Ravikran? Okay, okay, thank you. Okay, so once we get the elements of the table, then the procedure is quite simple. You just add these columns, column 1, column 0, column 1, and then this column 1, 2, 3, 4 will be RHS, column 0 will be on the LHS, and then you just equate these things to 0, because on the RHS we have 0, so RHS should be 0. Okay, now Fi cannot be 0, so that is why A0 plus A1 plus A2 will be 0. Then you get this a1 a2 whatever terms are there. Okay, so that is the procedure. Now let us come to the first question. Taylor series expansion is used in which type of discretization? So can you guys write down the answer on the chat box? It will be good if all of you can participate. Okay, so then only you can understand it better and you will be able to solve the assignment very easily. uh, and that is the main objective of conducting these sessions anyways. So they are asking in which type of discretization the Taylor series expansion is used. Okay, this I think I have answered during the discussion itself while discussing. Okay, I have answered it. Okay, this might be a little tricky, but I have answered it already while discussing. Okay, when I started with Taylor series, I see that only 3 people have answered. Okay. Huh. So you people might feel it is finite difference A and finite volume method. Okay. So I see different answers. Okay. I discussed this in the while talking about the Taylor series also. For example, if you consider a finite difference discretization, so you have an equation, say this is a partial differential equation, du by dx is equal to 3. Now this is your computational domain and grid. Okay, this is a one dimensional computational domain. This is only, there is only one dimension x, and you have divided into 4 grid points. Okay, in this thing finite difference method we call it as grid points, I minus 1, I plus 1, I plus 2, you have something like this. Now du by dx at I is equal to 3, you do a just a central difference scheme, I plus 1, I minus 1. So you are using the Taylor series. Okay, here this, from here to here you get it from Taylor series only. Okay, so definitely it is used in finite difference discretization, you will agree with me. Okay, now let us come to finite volume discretization. Okay, so in finite volume discretization what we do is slightly different. Okay, it's slightly different. It's more physical, but okay. By why I am telling it's more physical finite volume discretization is because you assume that this particular division you do and you create a volume around this element. Okay, that around P, which is I for me, I create a volume and say that this partial differential equation must be valid in this particular control volume. Okay. Now, when it is valid in this whole control volume, I can do a volume integral because it is applicable in the whole volume. Okay, so then I do an volume integral. Once I do volume integral, then I can use the Gauss divergence theorem, dou u by dou x into dv. I can write it as u into dA, that is using the Gauss divergence I have written. And here it is just 3 into delta v. Okay, this anyway delta v I have cancelled on the LHS and RHS. Okay, that is not an issue. So 3 dv I'll get 3 delta v, that is the volume of this element. Now u into dA, if I do, and remember that it is a the normal area. Okay, the normal area of x velocity, that will be only along this east and west face. Okay, small e and small w which I have written. Now u e minus u w I'll get it as, because I will not get u n minus us, I will not get here, because I'm assuming that the x velocity is flowing only from west and east control volume, because it is a 1D control volume. Okay, so I'll get only ue minus uw. Okay, if I had 2D I might have got un minus us also. Okay, and the delta v will be nothing but delta x. Okay, because this I have assumed infinity, so usually we assume 1 length of 1 in y direction and z direction. So 3 into delta x into 1 into 1, it will be the delta v, so it will be just nothing but 3 into delta x. Now this ue I will just do approximation. U at east face, I'll just write down u at p at u at e, the east control volume, divided by 2, that is the velocity at this east face. Okay, that is the expression for velocity. Similarly, I will write down the expression for velocity at the west face, u capital W plus u capital P divided by 2, and then finally I will eliminate p, the p will get eliminated, and you will land up with u e minus uw divided by 2 delta x. Now this is exactly similar as what you have got here. E is nothing but I plus 1, and w is nothing but I minus 1, right? So you have got the exact same expression, but you did not use Taylor series here. Okay, you did not use Taylor series, nowhere you have used Taylor series here. So if you see this example, you might feel that Taylor series is not required for finite volume method. But what if uh, dou square u by dou x square was equal to 3? Okay, what would happen in this case? You would finally land up with dou square u by dou x square. When you do this Gauss divergence, you will get up dou u by dou x into dA. Okay, dA you will get. Now you cannot apply Gauss divergence again. Okay, because you have dA. So you will finally land up with dou u by dou x at E minus dou u by dou x at W. Okay, if you had dou square u by dou x square. Now dou u by dou x at E, how will you find out dou u by dou x at E? Again you have to go for Taylor series only, if that was the case. Dou u by dou x at E will be found using u of capital E minus u of capital P divided by delta x. That is the central difference scheme. Okay, so in finite volume method also, if you have a second order partial differential, you will finally have to use Taylor series. Okay, so in finite volume method also you have to use Taylor series. Not every time, only in certain cases, but you have to use. Okay, I hope that this point is very clear. Okay, because you might get biased about the question. Okay, now in finite element method also a similar approach is used. I will not go into the details of this. Okay, because there is a lengthier derivation here. It's just that you do the integral again over this element, they call it as element in finite element method, and you should see that this dou u by dou x minus 3, the integral of that with a weighting function, it should go to 0. Now you have to find the weighting function by doing the interpolation of this so that it goes to 0. Okay, Now for this also you have to find out dou u by dou x at each nodes. Okay, this w of x will be then expressed as a dou u by dou x at each node, that is the corner you can say of this control volume. So that is called as a node in finite element method. It's a node of this element p. Okay, so there you kind of express this dou u by dou x in terms of interpolation of dou u by dou x at this particular node. So again you have to use Taylor series, right? How do you find dou u by dou x at that particular node? So again you are using Taylor series. Okay, so in all the methods in CFD, Taylor series is fundamental thing. Okay, you use it everywhere. You use the expression for dou u by dou x everywhere. Okay, so this should be clear to you. Okay, it's not only the finite difference method. Okay, so I hope that this is understood. Okay, if there are any queries you can write on the chat box. So all the answers A, B and C are correct. Okay, now let us go to a second question. It is quite simple. Higher the grid resolution, what will happen? Higher the computational cost, lower the computational cost, does not affect the computational cost. So what should be the answer for this? Grid resolution, try to link it with the camera. You have more number of pixels. Okay, higher the grid resolution. So what will happen if you have higher number of pixels? Yeah, many of you have already pointed it out. The computational cost will definitely increase. So instead of solving 16 linear algebraic equations here for a 4 cross 4 grid, I have to solve 64 equations. Okay, 64 linear equations. So I have to do a matrix inversion. Ax is equal to b. The size of A will be converted from 16 to now 64. Okay, so 64 cross 64 it will become. Okay, the size of matrix A. So definitely that is more computationally cost consuming. Okay, so yeah, A is the correct answer. So for let us see third question. Just carefully read this. Okay, for the structured grid, the grid line belongs to same family. The grid line which belongs to, it should be the grid line which belongs to the same family crosses only once for a structured grid. Okay, what should be the answer for this? Read it carefully. Okay, for the structured grid, the grid lines which belong to one particular family will cross only once. Can all of you participate in this? Because I see only two answers. Okay, okay, okay. One of you is telling true, one of you is telling false. Okay, so you have to read the statement carefully. Okay, it's a structured grid. Now let us see what is. Okay, sorry. What is structured grid? Okay, so you have a family of lines. Okay, f1, f2, f3, f4. They will intersect once. Okay, but f1 will intersect f3, f1 is intersecting f4. Okay, f2 is intersecting f3, f2 is intersecting f4. So that is what I have written: 1 comma 3, 1 comma 4, 2 comma 3, 2 comma 4. Never will you get 1 comma 1. Okay, here f1 will not intersect f1. Okay, it doesn't intersect itself. So even once also, that grid line will not intersect itself. It will intersect the other family of curve only once. Okay, f1 will intersect f3 only once. That is correct, that should be true. But here it will not intersect itself. Okay, the grid line which belong to the same family, f1 is one particular family, it will not intersect itself. Okay, so the answer should be false here. Okay, so it's false. So is this understood? For a structured grid, it will intersect the other family only once, but it will not intersect itself. Okay, for an unstructured grid, what will happen is that the one set of family of line will intersect the other set of family of lines multiple times. Okay, that is possible. I hope that this why it is false is understood. Okay, it will not intersect itself. The family of line f1 will intersect f3 ones, f4 ones, okay. F2 can intersect f3 ones, f4 ones, but f2 will not intersect f2, okay. I hope that that is understood. So the answer should be false. Now let us go to the fourth question, okay. Now consider the equation dou phi by dou x I comma j is equal to phi at I plus 1 comma j, phi at I minus 1 comma j divided by 2 delta x. What type of discretization is this? I think I have discussed this in detail in the beginning half an hour of this lecture. Okay, can you write down the answer on the chat box? How do we differentiate between forward difference, backward difference, central difference, and how do we define the order? Order is also very important. Okay, so what should be the correct answer for this? Okay, I see two answers. B, second order central difference. Okay, see, one thing is quite clear, that it is a central difference because we have both I plus 1 and I minus 1, right? So we have both left as well as right stencil, okay, at for I comma j. So it is a central difference. If there was only I plus 2, I plus 1 and all, forward difference. If there was only I minus 1, I minus 2, it would have been backward difference. So it's a central difference. So central difference, there are two options, first order and second order. Now how do you determine the order of this scheme? Okay, so for that you have to go to the Taylor series or the Taylor table approach to actually calculate this. How did you come up with this? Okay, so this is what I have written here. Okay, so you had phi of I plus 1 comma j and you had phi of I minus 1 comma j. Later on I will give a shortcut also how do you actually calculate the order without doing this all these things. Okay, now if you subtract these two things, these two Taylor series expansion, you will end up with an expression for dou phi by dou x. Okay, phi of I will get cancelled, I plus 1 I minus 1 is there, and then you are subtracting this, so dou square phi term will also get cancelled out. What will remain is dou cube phi by dou x cube to delta x cube by 3 factorial, which was there next. That will remain because here it will come plus and here it will come minus. Okay, so that will get added and you 2. Okay, so this will come up. Now if you see dou phi by dou x, you finally put this term on the LHS and bring this to the RHS. Okay, otherwise the other way around, you just bring this to this LHS. Okay, so what you will get, phi of I plus 1 phi of I minus 1 divided by 2 into delta x. Okay, now you are dividing by 2 into delta x everywhere. Okay, so 2 will get cancelled here. Delta x cube by delta x will become delta x square. Okay, delta x square by 3 factorial it will remain. So the minimum truncation error order is 2. The minimum truncation error has an order of 2. Okay, understood? So what should be the order? Then it should be second order. Okay, but this you this is useful if you have a very lengthy answer. For MCQ questions there is a shortcut. Okay, something you might have to kind of remember through an analogy. Okay, so we have first forward difference scheme. Okay, forward difference scheme. Now in this you have at I comma j you want to find out. Okay, now if you have say I plus 1 and you have I, you have two grid points in the finite difference formulation. Okay, this will give first order accuracy. If you have 3, you will get second order accuracy. If you have 4 points, you will get third order accuracy. So it is the order of accuracy. This is applicable for forward difference and backward difference also. Okay, backward difference. So order of accuracy will be equal to whatever the number of grid points you have in that formulation n minus 1, okay, it will be 1 less for forward or backward difference. For central difference the things get different. Okay, now if you have two stencils I plus 1 and I minus 1, okay, usually you don't have I in the central difference. Okay, you will get second order and you will never get third order. Okay, now here you will directly jump to 4. If you have 4, that is I plus 2, I plus 1, okay, I minus 1 and I minus 2. There are 4 grid points involved in the finite difference formulation. 4 grid points corresponds to fourth order accuracy. Okay, so order of accuracy will be equal to n directly, not n minus 1. Okay, this is how you determine the order of accuracy for a first order differential. Okay, similarly you can form the analogy for second order differential also. This I have just told for f dash first order differential. Okay, for forward difference or backward difference it will be n minus 1, whereas for central difference it will be n, order of accuracy will be equal to n. So that is how for MCQ questions you can directly answer instead of doing these derivations. But if you are quite interested to do, you can do this also, but this will be definitely helpful for your long format type of questions. Okay, and many a times you cannot remember everything, so you have to derive it. One thing is you can use Taylor table approach, which is quite easy, but although it takes time. Okay, and then come up with these equations, and this will be used in your code. That I will show in the last part of today's lecture. Okay, how we will use this to finally get the solution. Okay, I'll just show that at the last. Okay, so yeah, so B should be the correct answer for this question. So these type of questions you can expect in your assignment and in your exam also. Okay, so I hope that this is quite clear. Okay, how do you get this? Okay, if there are any queries in the meantime you can post on the chat box also. Okay, what is the order of accuracy of this discretization? This is a backward difference scheme, and let me correct, this should be delta x square. Okay, it's not delta x cube. Usually when you have dou x square you get delta x square only, you will not get delta x cube here. Okay, so this is delta x square. So what should be the order of accuracy? So let us not directly jump into the answer. Okay, let us see how we can calculate this. Okay, okay, let us not directly jump into the answer. Third order accuracy some Vikas has written. Okay, let us see what it will come out. But how do I get this? By looking at the equation it will feel very difficult. Okay, this how do I get this particular thing? uh, the approach which I follow for such kind of questions is just you do this calculation. You know how to expand phi of I minus 1 from Taylor series, phi of I minus 2 you know how to expand, you know how to expand phi of I minus 3 also. Okay, using Taylor series you will expand this phi of I minus 1, phi of I minus 2, phi of I minus 3. Then just do this multiplication. Just multiply 2 phi I minus, you multiply the phi I minus 1 expansion of the Taylor series with phi. You multiply the Taylor series expansion of phi I minus 2 with 4. Okay, then multiply the Taylor series expansion of phi I minus 3 with 1. And then do this then do this whatever is given this in this question, addition or subtraction. Then you will get dou square phi by dou x square, and in here addition you will get some truncation errors, and find the minimum order of this truncation error. That will give you the order of accuracy. So that is the procedure. So usually you should not remember anything. That is the main motive. Especially in the age of AI and ML, you are not required to remember anything. You should try to kind of derive this only. Otherwise if you try to remember you might forget and you might end up with giving wrong answer. Okay, so better to always derive and then just check. Okay, so yeah, so as I said I have done the same thing here. I have expanded phi of I minus 1, phi of I minus 2, phi of I minus 3 using the Taylor series here. Okay, phi of I minus 2 will be phi of I minus 2 delta x, because here I have 2, and here it will be 3 delta x, minus 3 delta x, 9 delta x square, because 3 delta x whole square, 3 delta x whole cube, okay, minus 3 delta x whole cube, sorry. So that is why minus 27 delta x cube it will come, okay. Now what do you want? You want this expression, right? So just multiply phi of I minus 1 with what do you say, minus 5, and multiply this phi of I minus 2 with 4, and phi of I minus 3 with 1. So if you just do that, even if you don't multiply this 2 with 2, you can't do this into 2. So it will come to 2 only, because that is what it will happen, okay. So then just bring it to the left hand side and divide it by delta x square. So if you do that, sorry, if you do that, what you will see is the minimum truncation error. So del 2 square 5 by dou x square is what you want, okay. So the minimum truncation error, it will have dou raised to 4 by dou x raised to 4, okay. And you will have delta x square coming in, okay, because this is the second derivative, okay. Remember, this is not the first derivative, okay. You are dividing it by delta x square, okay. So this will be a second order accurate scheme, okay. So why you might have said third order accurate is because of my previous discussion. Again, remember that I had discussed for first order. Okay. So what I had told is that if you have four terms, here you have four terms, right? And it is a what do you say, one-sided. Okay, it is a backward thing, backward difference. So you have total four terms, one, two, three, four. So if it was a first order differential, you would have got 4 minus 1, 3. The order of accuracy would have been 3. I think that is why you wrote it as 3, third order. But you have to look carefully. This is a second order differential. This is dou square 5 by dou x square. You have to remove minus 1 again. Okay. So that is the analogy I had discussed. I had told this is applicable for first order f I dash. For second order, you have to again formulate that analogy. Okay. There again it will become minus 2 actually, if you see. So it will be actually 4 minus 2. But anyway, you need not remember, that is what I am telling. You should try to derive it like this. That is more better approach. If you are really going to give some competitive exams and all where there is only MCQs, okay, so then you can make those analogies and go to exam. But really, if you are doing something interesting, some uh, long format exams, or say if you are really interested in coding, because ultimately these things will come into the code, okay. I will just show it at the end of this lecture. uh, so there you need to sit and you can derive. You have a lot of time, okay. Better to derive, okay. So that is what my approach is, okay. So yeah, so I hope that this is clear. Sorry, I think I wrote by mistake third order. It's again second order accurate, because here it is you are getting a minimum truncation error as delta x square. So it is a second order accurate scheme. Okay. Uh, hmm. Yeah, this you people can answer. This I have already given the answer in question number 4. What should be the answer for this? In order to get a fourth order accurate discretization of dfy by dx, minimum how many discrete points should be there? Fourth order discretization of first order derivative. This is, I mean, the first derivative, dou fy by dou x, f dash. So minimum how many discrete points should be there? Can you write down on the chat box what should be the answer? I have already discussed the answer for this. Okay. So they have not mentioned anything about forward difference you will be using, backward difference you will be using, or central difference you will be using. You have the freedom to choose any difference scheme here. Okay. The question asks minimum how many discrete points do you need? Okay. So first you should see which scheme I have to use. I have to use central difference, or I have to use forward difference or backward difference. So which type of scheme will you be using? Can you answer that? So you have the freedom to use central difference, forward difference or backward difference, which scheme you will be using to find dou f by dou x? Can you write on the chat box? I don't want answer for this question. I am asking a different question. Which scheme will you use for dou f by dou x? Forward. Okay. Why forward? See what I have discussed here. So if you are using a forward or a backward difference, the order of accuracy will be n minus 1. So if you have say 4 points, order of accuracy will be 3. Whereas if you are using a central difference scheme, if you have 4 points, you will get fourth order accurate scheme. So with central difference scheme, you will always get better accuracy with less number of grid points. That is the purpose why most of us use central difference scheme. Okay, we don't use forward or backward difference. We usually use central difference scheme. Okay, so the answer is we should use central difference scheme. Okay, I hope you understood why. Because with minimum number of grid points, with minimum of number of discrete points, we will get more accuracy with central difference. Okay, is that understood? Can you write down on the chat box if that is not clear? Okay, okay. So that is clear. So you should be using central difference. So I have written central difference formulation here. Dou f by dou x. Okay. If I use two grid points, discrete points, I'll get second order accuracy. If I use four discrete points, fi plus 2, I plus 1, I minus 1, I minus 2, I'll get fourth order accuracy. So using 4 grid points, I can get fourth order accuracy. So option number 1 is correct. Only you can have 4 grid points and you can get fourth order accuracy using the central difference. But your answer 5, which many of you wrote, is correct if you use forward difference or backward difference. You will be requiring 5 grid points, but they have asked minimum. Minimum is 4. Okay, minimum number of grid points because I am using central difference scheme. So option number A should be correct. Okay, I hope this is understood. Now it's already 7:20, so there are two more questions. I'll post this. These are also similar questions only, which we have already discussed till now. Okay, which of the following is a higher order scheme? Okay, you can just derive this. Okay, uh, based on our discussion and then get the answer. But what I really wanted to discuss, which is very important, is how do you put this in a CFD flow process? I mean, in a practical CFD problem, how do you use this finite difference things? You have learned so many things now: second order, first order, forward difference, backward difference, central difference. How will this really come into the actual picture? So that I want to discuss using a very small example. This will take only around 10-15 minutes. I'll just open up the platform for questions then. Okay, so just you have a small one dimensional steady state heat conduction problem without any heat generation. Okay, most simple problem. Okay, k into d square t by dx square is equal to 0. A heat conduction problem, very straightforward problem, and very straightforward analytical result is also there. There is no requirement to do CFD here, but just for example I have taken. In complex cases there will be no analytical approach available, results available, you have to do CFD. Okay, but just to explain the CFD process I have taken this example. So it is d square t by dx square is equal to 0 analytical solution, and I have the boundary conditions. Okay, at left I am having a temperature of 3 units, at right I am having a temperature of 0. These are say non-dimensional. Okay, don't worry about the quantity. Okay, so it's just 3 units and 0 units at the left and the right. Okay, I get a linear equation t is equal to ax plus b. This is analytical equation, and using these boundary conditions, x is equal to 0, t is equal to 3, so b should be equal to 3 and a should be equal to minus 3. Okay, I get t is equal to minus 3x plus 3. This is the analytical solution which every one of you will derive very easily Okay, this you have studied in heat transfer courses and all, whatever. It's very easy. Even if you know simple differential and integration, you can do this. I have just done an integration, d square t by dx square. Dt by dx will become nothing but a, and t will become nothing but ax plus b. Okay, so that is how you got it. So I hope this is very easy. You have understood this. In CFT, what do we do? We have already done the first step here. Okay, we have done the domain selection, we have done the grid generation. It's a 1D grid. I'm using finite difference method. I have generated 4 grid points, and in those 4 grid points, 2 grid points are boundary grid points. Okay, so I need to find the temperature at only 2 grid points here, okay, which are marked as 2 and 3. If it's not clear, let me just tell you, this is 1 2 3 4. Okay, so I have to find the temperature at second grid point and the third grid point. I know the temperature at first grid point and fourth grid point. Okay, so now I will use the central difference scheme for a second order derivative. Okay, so d square t by dx square, I need to find temperature at second and third. So d square t by dx square, I can write it as ti plus 1 minus 2ti plus ti minus 1 divided by delta square is equal to 0. That is the governing equation. So I have converted this partial differential equation into a linear algebraic equation now, because I have only ti plus 1 minus 2ti plus ti minus 1 is equal to 0. Okay, that is the equation. I will apply it at grid point 2 and grid point 3. I think I have started it here. No, 1 2 3 4 only. Yeah, 2 and 3. Okay, at 2 and at 3, what will I get? I plus 1 will be 3, I will be 2, and plus ti minus 1, 2 at grid point 2, it will be t1. T1 I already know it is 3. Okay, I have just written directly 3 here. Okay, it will be T1, but T1 is already 3, so equal to 0. This is the first equation. Okay, and the second equation for grid point number 3, Ti plus 1 will be T4, but T4 I know it is already 0. Okay, I wrote 0 minus 2 Ti, I is 3, so 2 T3 plus T2, that is I minus 1, is equal to 0. So I have two linear algebraic equation. This is the main crux. Okay, I have converted the partial differential equation into linear algebraic equations. These equation number 1 and 2 are the linear algebraic equations. Okay, this I can solve it. You already know how to solve these two equations to get T3 and T2. You do any method, you do matrix inversion, or you do whatever you want to do. So you will get T2 and T3. Okay, so through this procedure I have got T2 and T3. So let me just compare it. Okay, through exact. So let me just give an analogy again with video camera. Exact solution is like a camera with infinite resolution. Okay, you have infinite number of pixels. You can capture the temperature values at wherever you want. Okay, at whichever point you want, you can capture the temperature values. But that is not true for an actual camera. An actual camera will have finite resolutions. You can capture the light intensity, that is the color, at only some distinct pixels, right? You cannot capture in between. You can do interpolation, that is possible, but naturally you cannot capture it. Okay, so that is CFD. CFD is a finite resolution camera, which is the actual camera. An actual camera is also has a finite resolution. So you can only capture the temperature values at 1 2 3 4, and 1 and 4 point is boundary, you already know. You are capturing temperature values at only 2 and 3. Okay, T2 and T3 is what I have written here. Okay, T2 and T3. So T exact I can calculate anywhere. So I am calculating it as x equal to 0.67. That is the third grid point. I am calculating, it will come out 1. Okay, x is equal to 0.67. If you substitute 3 minus 2, it will become 1. It will become numerically. How do you calculate? It is nothing but T3. When you solve these equations, you will get T2 and T3. T2 I have got 2. I have got T3 as 1 when I solve these equations. Those are the values which I have put in here. Okay. So if you see T exact and T numerical, this is a very hypothetical situation that they are coming same. Both T exact, that is analytical, and the numerical, that is a CFD temperature, they are coming same without any error. But in reality, you will never get this. Okay, there will be some error with the exact solutions. Okay, when especially when you have a very high gradient, So d square t by dx square was some value, specified value, say 3, or the equations, you if you are having more derivatives, d square t by dx square plus dt by dx is equal to 3, or if the boundary conditions were difficult, if you had a, say, specified heat flux instead of specified temperature, there you had dt by dx is equal to some constant heat flux, insulated boundary conditions. Okay, so there you would deviate from the exact solution, but there also exact solution you could have calculated 1D heat conduction, you can calculate analytical solution, whatever may be the case. Okay, now you can understand that you are able to calculate the CFD result, and they are very close. Here they are exactly same as the analytical solution. Okay, but in general there will be some difference, but at least you are getting the same picture, right? Now where will this be useful? As I said earlier, when you have very complicated equations, which is generally true for our fluid conservation, the Navier-Stokes equation, they are very complicated. They are highly non-linear equations. They involve multiple variables. Okay, U, V, W, P. They are non-linear in nature. So those cases you will not get directly analytical solution. Analytical solutions for full Navier-Stokes equations has not been found out till now, and really, if an analytical solution is found out for Navier-Stokes equation, then there is no need for CFD subject only. Okay, so so CFD subject will only have to close. Okay, so till now Navier-Stokes equations nobody has found the analytical solution. Okay, so there we need to do this discretization, come up with a linear equations, solve them. Okay, this is the whole process of CFD. Okay, so I hope that you have got a small hint of this. So here I have just done a hand calculation. Okay, just I had two equations and two unknowns. Now what if I had four equations, four unknowns, 10 equations, 10 unknowns? Then I cannot do hand calculations. I have to use a computer. I have to do a matrix inversion. I have to use a computer code. There, then the coding part will start. Okay, so that is why I told this week we will do some pen and paper work. So next week when we get a bigger equation, we can start doing coding. Okay, so before that this will serve as a fundamental thing. So that is why this is very important. If you have understood this, then coding is very easy. Let me tell you that the CFD coding part, the foundations are important. Apart from that, it is just the normal coding. If you are good at normal coding, which you can understand, which you can quite grasp it also as the time progresses, these things are very easy. So okay, so I hope that there are no if there are any queries, please let me know in the chat box. Okay, are there any queries with respect to this exercise which we have done to understand the I mean the procedure for CFD? And in general, in today's lecture, if there are any queries, or if you have another query regarding this peaks content, you can ask that also on the chat box. Okay, because only some around 10-15 minutes are remaining, so we'll try to wrap it up. So if you have any questions, please ask. Okay. Wait a minute, I'm just checking my messages. Good evening, sir. I joined only on last Sunday. Yeah, so last Sunday. Acha, so this is week two contents. Okay, so in week one we have just seen basics of CFD. I mean, what is CFD? What are the applications of CFD? And why do we really need to learn CFD? It was just, I mean, just it was more of a theory kind of thing. We did not start with any derivations or these differences. Only this week has some mathematical content, and it will grow by next week. Okay, so in first week it was very basic things, why we need to study the subject and what are the equations which are there in CFD, what are the basic equations which are there, so that you can just go through. And okay, I think I had posted it earlier also. I have done a similar recording for week one also. You can go through that video, you will understand. Okay, I have just posted it on the chat box. Okay, the week one lecture videos also, you can go through that. If you go through that, you will get a overall summary of the content. And in this particular Google Drive, I have put up the lecture slides also. Okay, you can go through the lecture slides also for week one. Okay, will there be an extension on submit assignment? That I don't know. That you have to contact the NPTEL support team. They will let you know whether they can extend it or no. I think it was the Wednesday was the deadline as far as I know, and tomorrow it will be the deadline for week 2 assignment. Okay, so week 1 assignment deadline might have already passed, so you can just contact them, ask them. Okay. Any other queries regarding this week's content? And if you have not understood anything, you can maybe post on the chat box. Yeah. This equation is definitely elliptic in nature. Last week also we have discussed this. What is the nature of equation and why do we really need to understand the nature of equation? That is to determine the solution scheme which we have. In general, the transient equations, if we have dou t by dou t, that is the temperature rate. Okay, then it will be a parabolic equation, and then we have to select suitable time marching schemes also there. Okay, so that we will cover later on when we come to next week's content. But yeah, definitely it will be parabolic in nature, as you have said. While solving assignments, will there be a limit of say 1 hour? I don't think so. I don't think so. There is a limit of time for solving your assignments. Others can answer this also on the chat box, but as far as I think, I don't think there is a time limit. Okay. Order of accuracy can be like 0.5, 1, 2, 3. Okay, this seems to be a good question because I also really don't know, but let me just try to answer it from what I already know. Okay. So ideally, it shouldn't be a decimal because you kind of find this truncation error. Uh, so how can it be a decimal? In which situation can it be a decimal? This delta x raised to some decimal has to come. Uh, so I don't think in any of the cases you will get it as a decimal. I mean delta x raised to something decimal. So until and unless you end up with delta x raised to something. Delta x square. No, I don't think you will get a decimal order of accuracy. That is what I feel. But I will just write down this point and I'll just clarify it in the next week. But as of now, I don't think mm, decimal order of accuracy is possible. I am not really sure, but as far as I feel, you should get delta x raised to something here. Only then it will be order of accuracy as okay. In practice assignment, you have that question. So I don't think it should be there, but just reach out to me also in my this is my mail id. I'll just clarify it on my mail also. You can reach out. I'll just check once, but as far as I think as of now it should not be. The order of accuracy should not be in decimals. I cannot imagine a situation where it will be a decimal. Okay, that is what I feel. Okay, okay, I'll allow you to speak. Just wait a second. I'll just what I'll do, I'll just stop sharing the screen. Yeah, I think now you can ask. Yes.
Of the partial differential equation.
Hmm.
In one of the lectures, it was mentioned this is the way to check whether it is hyperbolic or elliptic.
Mm-hmm.
So
Yeah.
effort is suppose in that also it was shown in Laplace equation that
Hmm.
was elliptic in nature.
Yeah,
But
Laplace
in
equation is elliptic. Yes.
in the next line, dou t by dou t line was written and like transient for transient case,
Ah.
say del t by del time was written and then the research said that it is now like parabolic.
Yeah, it is parabolic. Yes.
But when we go back to the checking the e square minus 4ac, it is still not less than 1. So,
P square
how
minus
that
4ac will come to 0, no?
then it will become parabolic.
Yeah, yeah. But you are telling it is not becoming 0.
Sir, Laplace equation, if we check by that equation, it is like less than 0. That's why it's elliptic.
Huh.
So if I add dt by dt, say,
Huh.
then how that b square minus 4ac is changing? It is the same negative, but we are calling it like a parabola.
No, no. Temperature will also be an independent variable, na? So you should check for like dou t by dou t plus dou square t by dou x square only. X and t are there independent variables there.
But logically, I'm getting this value.
Huh.
Okay, it can be a marking problem,
Huh.
but when we have a very thumb rule of that, we have a general PD equation where the first term is like a d square t by dx square plus mixed derivative, then c. So we have A, B, C, and the rest of the things do not come in the calculation of nature of the equations. So
No,
B
I.
square minus 4 is
Hmm.
always a negative.
No, I think why you are telling that is because you took first d square t by dx square plus d square t by dy square is equal to 0. You treated x and y as independent and then you calculated b square minus 4ac. It was coming less than 0. So you told elliptic. Okay, now you are adding dt by dt. Okay, and then you are telling it will remain same, that it will remain less than 1, 0, right?
Yes,
But no, you have to select t as also an independent parameter now. Okay, so you have to ignore one spatial coordinate then. Okay, one spatial and one time coordinate. Okay, so then based on that, the equation will change. Now you have like uh, just let me go through that week's this formula. I have it. So basically dou t by dou t, there also it will be like x. Now t will be like x and then you have a spatial coordinate that will be like y. So these are two different independent coordinates. So from that you can get it. But I don't know whether I have that particular equation. I think it will be there on Wikipedia also. No? Nature of nature of PDE, I think. Here I have not given it. I think it was there in the previous week's content. Previous week's content. So what I am trying to tell is basically you have dou sorry dou t by dou t. Okay, this is one independent coordinate plus dou square t by dou x square is equal to 0. Okay. So mainly you have to identify what is A and what is B in this particular equation. Okay, so through that you will get B and A, but I'm just trying to see how do you define B and A. Classification of partial differential equations. Yes, this is the equation A into dou square 5 by dou x square. Okay. Okay. So you are telling dou phi by dou x will be in, so it will not interfere with b square minus 4ac. Yeah, I understand your question now. Okay. Because it is in d term. Okay, d is nothing but associated with dou phi by dou x. But uh, b is 0. See, the thing is, that is what I am trying to tell you. You have to take all the spatial coordinates as one unit and then the time as one unit. Okay, so then what will happen is that b is anyway 0. Do you agree? B is 0, right?
Yes.
And then what will happen is that c will also become 0. Okay, you might be thinking as c is not 0. Okay, so when you take all the spatial coordinate as one unit and the time as one unit, because now that is a separate independent unit when we have a transient term. Okay, so you should ideally get like dou square t by dou t square, so that doesn't exist, right? So c is 0 in that particular case. So you is my screen visible to you? Wait, I think I have not shared my screen. Oh, sorry. Yeah, my screen is visible, na? No.
Yes, visible.
So now in this particular case, B is 0, C is also 0. Okay, so now B square minus 4AC is 0, and that is why it is parabolic. Now you might say I will add dou square t by dou y square, but that I cannot consider it as an independent variable. I need to have dou square t by dou t square, only then I can say C is something. Okay, so in this particular equation, it will become a parabolic equation because C is also 0 and then B is also 0. But if you have only purely this thing, Laplacian equation without this, then Y is a different independent quantity. And then you will get, I think, less than 0 because A and C are some values, whereas B is 0. Negative value you will get, I think. So, but here it is a different independent property and spatial coordinates together are one independent properties. So that is how we treat them. Because we are marching in space time, because those two are uh, two independent properties. That is how we kind of consider it. Is that clear? I mean, that is the
Yes,
way.
got it. Okay.
So
Thank you.
okay, so that is why it will parabolic, and in many Navier-Stokes it will be a combination of all. It will be combination of elliptic and as well as parabolic in Navier-Stokes equation. And many times, if we have a high advection term, it will become hyperbolic equation also. Any other queries? Let me see the chat box. Share the link. Which link? Which link do you want? I've shared, no? Video or not? In this video, it will be available in this particular link. Okay. Are there any other queries? Okay, if there are no other queries, okay, thank you for attending. Okay, so from next week we will start probably with coding depending on the content. Okay, so this week I just wanted to explain before going into coding how we do it on a pen and paper. From next week I'll try to take up an example and then just show the code and write the code and show it in front of you, and then maybe I'll share that code also with you people. Okay, so that is how we will be going on apart from solving the questions.